Together with Toni from Reddit. We are both from the Kuryr project. Toni is a PTL. And we are going to talk today about the recent addition to the Kuryr project, which is integration with one of the most popular containers orchestration engines, which is Kubernetes. I'll provide you with a brief introduction into the project, explain the main features that we support, deployment models that we support, and explain the basic architecture of the integration, and then Toni will dive into the technical details of the integration. So what is the main challenges? Now we're in the time of the cloud-native workloads, which means that most of these workloads are based on the 12-factor application methodology, which on very, very high level means that the state is separated from the infrastructure or the capacity, and actually there is no way to provide cloud-native application without this clear separation. What seems to be the true in this, that also the VMs are too heavy and too big and take a lot of time to spawn them, so most of these workloads are based on containers. Usually the application architecture follows the microservices paradigm, which is taking place of the previously used the monolithic approach, and such applications are highly automated and self-healing, and obviously all of this imposes challenges on the application networking versus the more traditional ways that it used to be. For those who are not familiar with the Kubernetes, I will provide a very, very high-level overview of the Kubernetes in order to explain later what we map with the Kuryr to the Neutron model. So basically, there is a cluster of nodes managed by Kubernetes. There are worker nodes, either physical or virtual servers, where the workloads are placed and running. There is a master nodes where the control plane of Kubernetes is running. So if we take a look on the main components of the Kubernetes, there is the etcd used as the cluster Kubernetes cluster state storage. There is an API server, which is the only component that connects directly to the etcd. Other components can direct and get information about the state and model of the cluster only through the API server. So API server is the main management facade of the Kubernetes. A scheduler is responsible for placing the workload, taking a look on the requirements of the workload and the current state of the cluster and the machines, and then decide what worker node will run the specific workload. The controller manager is responsible to take care of different replication sets requested by users and make sure that the desired state is matched with the actual state. On each worker node, there is the continuous runtime. Here is a Docker, but it can be something else. The kubelet is the main daemon running on the worker node, which is responsible to watch Kubernetes API changes and then make sure that requested local workloads are running and report their health state. And there is also the Kubernetes proxy, which is a basic network proxy component that makes sure that the services capability is supported. So it just very briefly like a load balancer, but we'll explain it later. The basic Kubernetes data model, we can see here the main entities. So pod is a basic scheduled unit, which is basically set of application containers that share volume, and this is a minimal unit that Kubernetes operates. So it's basic deployment and scheduled unit. The service is a stable name and stable IP address. This is abstraction of the group of pods and some policy how to access them. And the namespace is a virtual cluster which allows which allows different teams and different environments and different projects to share the same physical cluster. As you can see here in the diagram, there are different layers. So in this case, there are 3-tier application, and for each tier, we have also the replication set, which consists of pods, and we have the service which has specific IP and port, and also name to enable the DNS support. And usually the tiers are talking with each other is just through the service IP, because the pods IP are something that you cannot count on. So what is Kuryr Kubernetes project motivation was? What we saw is that in the OpenStack environments where there are already virtualized workloads, users want to deploy containers, usually managed by different container orchestration engines, such as Kubernetes, Mesos, or Docker Swarm. But actually, there is no proper way to combine the workloads, which may consist from both VMs and containers, sometimes also bare metals. And while this is possible, there will be probably different layers and several orchestration engines that should be operated in the same cloud environment in order to fulfill all the requirements with these mixed loads. Also, in some cases, especially for security reasons, the container cluster is deployed inside virtual machines, where each project or tenant gets its own virtual machines, and containers are deployed inside it. And if it goes natively, so there is a networking layer that connects its virtual machines, and there is a networking layer connecting the containers. So this may lead to degradation in performance and latency, because if we use the overlay, so there will be just double encapsulation. And if even those parts can be mitigated, there still be several orchestration systems that should be operated, and just monitoring and troubleshooting and find what is going wrong or get statistics. So it can become a nightmare for the operator of such environment. Another way which motivates us to go to this project is that sometimes there are already existing applications deployed in the cloud, and they want to be refactored and moved to a more cloud-native approach. But it's quite difficult to do it in one step. So some parts can be rewritten while other parts can be still running in virtual machines. So having Neutron as a networking layer that which allow to connect together those virtual machines and containers on the same network can allow very gradual and smooth transition to the cloud-native container-based workloads. Another piece that is that we are dealing under the Kuryr Kubernetes is the storage part, the Fushi project, which will allow the bare metal storage, OpenStack storage support for the containers. So the mission of the project is to provide Neutron-based unified networking that will allow to connect together containers, virtual machines, and bare metals. With Neutron, we have different backends already supporting Neutron APIs. So having one integration with Kuryr binding the Kubernetes networking to the Neutron, it actually supports many different options for your SDN choices. So for now, for example, it's quite easily to take the OpenStack Neutron reference implementation or Dragonflow or OpenControl and just use it with the Kuryr Kubernetes integration. Having Neutron as the Kubernetes networking backend will allow also various virtual topologies, not only put containers on the flat network, like it's supported with the Kubernetes native networking mode, but it will allow to mix L2 and L3 connectivity, mixing different workloads. And as I mentioned before, it will allow an easier transition to the microservices-based applications and connect the virtual machines and containers on the same infrastructure. So one of the use cases that we support is the bare metal use case, where your containers are deployed on the bare metal machines. This is usually used to provide better performance and when security is not the main concern. So maybe some testing clusters can use this model. So in such case, there is an OpenStack controller where components that we use, and I'll explain it in more details later, is just Neutron server and Keystone. Neutron server for the networking, obviously, and the Keystone for authentication. There is a Kubernetes master with all the components I mentioned before, but we have an additional component from Kuryr controller, which is part of the Kubernetes control plane for the sake of this integration. And on each worker node, we also have the Kuryr CNI Driver that is responsible for the local binding of the pods. And we have on each worker node also the Neutron infrastructure based on your choice. It can be OVS, OVN, Dragonflow, ODL, whatever that can bind your containers. But from the Kuryr perspective, it doesn't matter because it just gets the information required for the binding and performs the local binding of the pods, and no access to the control plane of the Kubernetes, in addition to already existing connectivity of the CNI to the API server, is not required. For the pod in VM case, which we also call the nested case, when your containers are deployed inside virtual machines, this case is usually used when you need the proper separation between different tenants. So the tenant gets its own virtual machines, and the security and different policy can be applied on the level of the tenant on the virtual machine, and then no mix and match between the containers from different users. So in such case, we'll have the control plane also deployed inside virtual machine, and we'll need the the Kuryr Kubernetes controller to be deployed as an administratively managed virtual machine, having the Kuryr controller inside. And actually, this is the only VM that will need to access the Kubernetes API and the Neutron server. And as you can see on the worker node VM, we have the same as with bare metal case, the Kuryr CNI, which will be responsible to do the local binding only. What we use for this nested case is the capability introduced in Neutron since Okata release, the trunk port, and Toni will explain it in details a bit later. There's also some mixed use cases when we have both virtual machines and nested containers and maybe bare metal containers connected through the same networking infrastructure. This case, for example, when you can use Magnum to deploy a Kubernetes cluster. So there will be virtual machines at the Kubernetes nodes, but maybe there are some pieces of your application already deployed as virtual machines. So you can use the existing Neutron network and bind the newly created containers to already existing network. And for supporting this nested functionality, as you can see inside VM, there is lightweight tagging layer. So it can be either trunk port, and there is also existing work, and I think it's about to be merged to support Mac VLAN-based connectivity of the nested containers. So what is the supported functionality we have right now? We support the native Kubernetes network mode, which is basically the flat network, where each pod have IP from the cluster subnet. This is modeled to support the single tenant. We're also looking into the work done currently in the Kubernetes community to support multiple networks, and basically this will allow also the case of multiple tenants, we try to be aligned with the community, so not to reinvent the wheel or not to go to the opposite direction from the Kubernetes community. So for now, we just align with the basic Kubernetes mode. We also support the Kubernetes cluster IP service type, which is the default service type in Kubernetes, internal service. Just as we saw in a few slides ago, with the basic applications that above of each group of pods, we have the service just to make the stable IP and name to access between different tiers. But there is already work to support the load balancer service type, which means the service will be it will be possible to connect to this service from the outside of the cluster. And we also support the bare metals and the pod and VMs and the mixed environments. So what is the Kubernetes Kuryr architecture high-level view? We already saw that there are two components in the integration. One is a Kuryr controller, which is part of the control plane of Kubernetes. So logically, it belongs to the master node. The Kuryr controller responsibility is to watch the changes of the Kubernetes API. Currently, it looks for the changes on pods, services, and endpoints. Once a relevant change occurs, it just goes to the Neutron server and creates the relevant object. So each pod is translated to the Neutron port. Service and endpoints are translated to the Neutron load balancer model. We use Neutron LBus v2 API, which is the most updated API, so no need to go for the v1. And currently, reference implementation is HA proxy. The next step, we are going to support the Octavia integration. So coming back to the Kuryr controller, it's responsible to create the relevant Neutron entities, and then it annotates the Kubernetes resources with all the required details to perform either later local binding of the pods by CNI or later cleanup of the resources when, for example, service or pod is removed. So such information like IP, MAC address, and UUID of the ports is the information that is entered to the annotation of these entities. What we decided to do is just to use as much as possible the OpenStack infrastructure for all the components. So we use in the annotation the format of OS-VIF library entities, which is also the Oslo version object. So it will be much easier to do the updates and support backward compatibility between different versions of our integration. And then if we look in the Kuryr CNI part, so as we mentioned before, there is no need for the Kuryr CNI to get access to the Neutron server. All the information that it requires in order to do the binding of the pod, it just gets in the annotation of the pod object. So when it gets a notification from the kubelet daemon about new pod to be created, it will check the annotation required to do the local binding, including the VIF type. So basically, it's very similar to what Nova does with VIF plug capability, and then create the pair of virtual interfaces. One will go into the container, into the pod namespace, and the other will be just plugged into the Neutron infrastructure. So in this diagram, this is the OVS, because it shows the basic reference Neutron implementation. Now, for more detailed view of the integration, I'll hand over to Toni.
Can I ask a question, please?
Yes, sure.
How the network works between two pods that secret VM? I know that there is a Flanel, but Flanel can work with Kuryr.
So for now, we just map this to the same Neutron implementation that is used in the deployment. So it just what you decide on your deployment, you can use the OVS reference implementation, for example, and then it just connects your virtual machines and your containers. But Toni is going to explain how the nested binding works, so maybe it will answer your question. If not, we can come back to this question later.
Sure. I have the... All right, so how many of you operate an OpenStack cloud with Neutron? All right, and how many of you use Kubernetes? Okay, and how many are looking to use Kubernetes? Okay, very well. Good, good target audience. So as Irena explained, the controller is what is watching the Kubernetes API server, and I will not repeat what she said, and then annotates. Then from Kubernetes 1.6, support for role-based access control was added, so that all the components that interact with the API should have some degree of permissions and policy that applies to them. Here you can see the example. So the Kuryr controller, what it does is basically update and watch. So it has these different roles. I can. So here we have some of the resources that it touches. Actually, some of them are future-proofing, like nodes and so on. In case we use SRIOB, we're probably going to keep and maintain the SRIOB pools, the virtual functions in such objects. Then the CNI Driver, what you can see here is the notation that Irena was talking about, what kind of information is stored. This is a bit shortened because part of the OSB is it's an Oslo version object, and it has information about which version it is and so on. But the important thing that you can see here is that you have the information about the port, the Neutron, the subnet, the IP addressing, and so on. So with this, we have all that we need to perform the plugin. So if we look at how the plugin happens at the bare metal, here you can see a bit the interaction between the components. If you look at the left-hand side, you will see that the user creates a pod, and this generates events to all the watchers of the API. In this case, there will be the kubelet, probably the controller manager for putting the secret tokens. And of course, if there is Kuryr, there will be the Kuryr controller. And that means that all the actions that these elements or that these components have to do can happen at the same time. The synchronization point is in regards of the actions they perform back to the API. So you can see that the Kuryr controller creates a port, and then it will be checking if it is active before it puts a further annotation of it being active. First, it will annotate that the port is not active because nothing has activated it, but the kubelet will have created the infra container pod, the infra container for the pod, and it will have called our CNI to networking. Our CNI will connect to the Kubernetes API. It will try to watch for the content of the beef. And when it sees it, it executes the binding using the standard OSBIF pluck method. And this will trigger the OBS agent to do the coordination with Neutron. This depends, of course, on the backend that you're using. And once the controller sees that it is active, it will put a second annotation, and the Kuryr CNI will see it and will know that it can return, and that all the containers that will be started sharing the same namespace as the infra container will have immediate networking, so no packet will be lost. So in the case that you're doing pod in VM, so the question that we had earlier is how do the pods that run inside different VMs communicate? What we use is the Neutron ports, and since there is no binding to be done at the VMs anymore because in the VMs there is no OBS agent running, what happens is we just create a port, so the Kuryr controller, this looks more or less like before, but the Kuryr controller, what it does is it creates a port, then it says, okay, this port should be a sub-port of the trunk port that is serving the VM. So the work is performed by the agent that runs, the Neutron agent that runs at the host level. It creates a bridge called the trunk bridge. It's another OBS bridge that gets passed to the BR-int. And then when this work is done, you can get the information that the port is active. It will be active at the host level. Nothing is communicating to it. But at that point, we can update the annotation, and the Kuryr CNI can have the VLAN device that it created for the pod already working. looking now more at the services, what we see is that in a typical Kubernetes deployment, you'll have funnel for the pod-to-pod communication, and then you'll have kubeproxy for the services. It will have IP tables that will say, okay, this service IP goes to this pod that I have on this machine, or to this pod that is in another machine. In our case, how we map that is we take the cluster IP that is determined by the Kubernetes API, and we create a VIP on a Neutron load balancer for that. Right now we use Neutron LBus v2, but the idea is to move it to Octavia. And then we create a listener for each port that the service wants to listen to. And then a pool, and the members are all the pods that you keep adding. So if you move the replicas, the members of the pool keep resizing, as you would expect. So, sure, go ahead.
Do it for every service, or one that load balancer?
So this is what you get. What you see here on the left-hand side of the Kubernetes is Kubernetes service, and this is the cluster IP type. For the load balancer type, what you get then is that you get assigned the IP of the node. So you have usually an external load balancer that gets redirected to that node, and then that node has an IP table that takes you wherever it needs to be. Well, in all the nodes, in fact, if I remember correctly. So in our case, for the cluster IP type, it looks like this. You have a load balancer from Neutron LBus, and the only difference for us, for implementing support for the load balancer type, is that we just assign a floating IP to the VIP that we have there. So this applies to both. It's just that for the load balancer IP type, you have an extra assignment of a floating IP. So here is how this is created. It looks very similar to what we saw before. The flow is always Kuryr controller sees something and does something. In this case, it sees that the service and endpoint resources are created and updated. It reacts to that, creating the load balancer. Then it has to wait for the load balancer to be active. Then you create the listener. Then you create the member pool. Of course, after each of these things, in the reference implementation of Neutron LBus v2, it goes a bit on maintenance mode, and then it goes back to active. So we wait for these things so that there's no lost, no races on the updates. And finally, when everything is ready, we annotate both the endpoints with information about the load balancer and the service object. So here you can see a bit about scaling information. What we did is, since a lot of the slowness that you could get is going to Neutron a lot. So what we do is we move to bulk operations. So if you need, I don't know, like you estimate that you will need 100 containers in burst mode. So what you do is you create a pool of 100 Neutron ports, and when you need them, you will have them available, and all that dance of the OBS agent and the binding and so on doesn't happen anymore because they are already bound in the machine. And this is a demo that we did so that you could see a bit like what is typical deployment I work with, which is two big hardware machines, this R51003 and R51002. This is a Nova Compute, this is the controller, and this is the services that we use inside. And then I use 3 VMs, one master for Kubernetes, and then 2 worker nodes. And all the communication happens. So you don't need Flannel on top, and you shouldn't use it if you use Kuryr, in fact. And instead what you have is that the pods just use, each pod gets a Neutron port, so anything that you can do with the VM with their Neutron ports, you can do in this case, just such as adding security groups to them, modifying the rules, and so on. So for what's next, and I'm finishing with this, is the load balancer type. As I said, it's just adding a floating IP. Then the pool support is being merged this week. And then things that are a bit further down the line, which are ingress support, like ingress policy ingress and policy objects, translation, and then some management CLI, so that if you want to manage the size of the pools and so on, you will be able to do it from the CLI instead of having it happen in a reactive mode if you already expect some kind of patterns of workloads. So I would encourage you to help us and help driving the requirements, and not just the requirements. If you want to report bugs or you have questions about integrating it with the current Neutron backend that you have, you're welcome to come to the Kuryr IRC meetings or send something to the mailing list, and just help us move this forward and make it fit your requirements. Thank you.